the energy at this point. So there is some calculation of energy in the Euclidean space, and then there is a closed loop which finds the best shift, which minimizes the energy. Okay, so far we are doing something we call shaping. But how do we do coding? So we don't, shaping is not enough. We want also that each point we are transmitting would be with redundancy, would be immunized to error, to noise, sorry. So how we are going to do that? We don't want that any possible points near this, let's say we can draw artificially some Voronoi region around the origin which represent these points with minimum energy. We don't want that all the points here will be valid code words, because this means that we are not in, we don't have noise immunity. So what we are going to do in practice again, instead of playing with nested codes and nested lattices, what practical people would say, okay, I don't want that all information bits would be valid, so I'm putting here another block which is adding redundancy. So it would be error correction code. Let's use the same term as I used here. And the information bits will enter here. Information bits. And at this point we get coded bits, or since we thought about this point as a point which defines a syndrome, which carries the information, what we are doing is we are diluting the syndrome. So before adding this block, all the syndromes or all the cosets were valid. By doing that, we are doing syndrome or coset dilution. I like to think about it as syndrome dilution because this is syndrome dilution, because this is the meaning of this input. It defines the syndrome. And this together, and again here there is some G double tilde and H double tilde. These two codes together are generating something which amounts to this nested structure. So maybe this is another example where at least for me, it's easy to talk about these geometric structures which we call the nested lattices and binning and all that, cosets. But in the end, in the practical scheme, it may look different. There is a different way to achieve the same target. Okay, I hope this was clear. And it should have been on the slides, but I need to improve the presentation. Okay, so let's now assume that, thank you, that everything here on the slides is in this language of nested lattices, but in practice there are ways to implement it. Okay. So what would be a scheme which does lattice, a scheme that does lattice shaping and encoding and decoding, how it should look like? And as I said, you can call it also Voronoi modulation. And I like Dieter, so I want to show you where Dieter enters the picture. So first of all, the points, the information bits are mapped to a point to a fine lattice point inside the cell of the coarse lattice. And the pictures always show Voronoi cell, but as I said, usually it can be any fundamental cell. And usually it's actually easier to enumerate points in terms of parallelepiped cells and not as in terms of Voronoi cells. So this is just for illustration. It looks like a Voronoi cell of the coarse lattice, and the points of the fine lattice. These represents the message. Or you can think about it that each message is actually represented by a coset in the quotient group of lambda 1 over lambda 2. At this point, we have a vector, which is represent the coset. We add Dieter and do a modulo operation, modulo lambda 2. And here it is important that the modulo is with respect to the Voronoi And the reason is that here we measure energy. And we want to get here minimum energy. So let's remember that the crypto lemma guaranteed that if we have a vector v plus diter modulo lambda 2, this is uniform over the basic cell of lambda 2 independent of v. So if we are selecting in this model, if in this modulo operation we are working with Voronoi, we will get that the average power for any message we transmit, average over the diter, is always the second moment of the coarse lattice. So the second moment of the coarse lattice plays the role of power. Okay. Now we enter the channel and we need to decide how we do the coding.
Sorry,
Sure.
is this true even if you don't add the diter?
No, this is true for random diter. So this is the crypto lemma. Crypto lemma guarantees that for any fixed message on the average over the diter, we guarantee the power. And of course, yesterday there was a question: what if the diter is not random? If it is not random, then each message will have a different power. But for analysis, it will be very nice for us to assume that there is indeed diter which is random, and it will symmetrize everything. So all the messages will have the same power, and will also have the same probability of error, as we shall see, and many nice things.
If it's not random, the average power is not the same as one.
Right. If it's not random, then it means we have some kind of, instead of uniform distribution over the Voronoi cell, we have uniform over discrete points. So at the highest SNR, it's almost the second moment. At lowest SNR, it is certainly not. Because at lowest SNR, you can think that I have a certain cell and I have like 3 or 4 points inside it, and I'm taking uniform distribution about on that. It doesn't represent the second moment of the lattice. Okay. So decoding. So according to the classical digital communication, decoding means doing maximum likelihood. So we go over all possible valid code words, which are v plus diter modulo lambda 2, go over all these possible v's, all possible concepts, and we find the one which is closest to 1. But this is complex. Why it is complex? Because we need to take into account the structure both of the fine lattice and the coarse lattice. We would like to simplify matters by doing decoding when forgetting about the shaping lattice. We only want to think about the fine lattice, which is the coding lattice, when we do decoding. And then comes the idea of lattice decoding. Lattice decoding tells us that we first look for the closest point in the fine lattice to y, and we ignore the shape. And in the end, we do modulo lambda 2 to get a point, a valid point. The last modulo lambda 2, by the way, is not to the Voronoi, but it is just to a representative set of the cosets. This is why this last operation is simple, it's not complicated. It's not a nearest neighbor operation. Only then this operation is hard. So we can call it unconstrained search, and it is supposed to be easier. And as I said, there is the division between what I am interested in and what the coding people are interested. It's a question in the end how to really show that for a given nested lattices you can make this operation much easier than the maximum likelihood. But at least from intuitive point of view, it should be simpler. And this people call this lattice decoding. Another possibility is something that is known as coset decoding, which means that since all the points of a coset represent the same message, so it wouldn't be correct to find the one point which has the maximum probability, but to sum all the probabilities of the coset and then decide which coset has maximum probability is the most likely. This is a little bit more complex, because we do need to take into account the lambda 2 structure at the coding, but it is still not as complicated as maximum likelihood. In the end, we don't need to do that in order to show that as n goes to infinity, we achieve capacity. So this is just, let's say, an intermediate solution for practical schemes. And okay, let's skip this question. So let's see what we have here. We have a transmitter which does this operation, takes a representative of the coset, add beta modulo lambda 2. This modulo lambda 2 must be to the Voronoi region. There is a channel which adds noise, and there is receiver, which we can think as if it was first subtracting the beta, doing modulo lambda 2. This modulo is simple, as I said, not Voronoi. It can be to any fundamental cell, any set of representatives of the cosets. And then in the end, we do this decoding to the nearest lattice point. And there should be here modulo lambda 2 also in the end. Okay, so this is related to your question. There you go. But again, at the receiver, the modulo lambda 2 operations are simple because they don't have to be Voronoi. So let's see what it means in terms of power. In terms of power, we already know it's second moment of the coarse lattice. What can we say about rates? So because of the distributive property of the modulo operation, which we mentioned yesterday, A plus B modulo lambda, and modulo lambda on B, and then modulo lambda on everything, it's enough to put one modulo to get the same result. We can forget about the first modulo for the sake of analysis, and we can say that the entire system, including the channel and the coder, is equivalent to this picture. And then it is easy to see what is the probability of error and what is the rate. So the rate is given, as we said earlier, by the number of cosets, which is just, or the number of points of fine lattice inside the coarse lattice cell. So it's just a ratio between the volumes. And we can translate this expression. Okay, then I'm taking log on the basis of 2 to get bits, and I divide by the dimension to get bit per channel used. And I want to relate that to powers. So we remember from the definitions yesterday that the normalized second moment, G of lambda, was defined as a second moment, lattice second moment, something I denoted like that, divided by the volume of the lattice raised to the power of 2 over n. And the NVNR, the normalized volume to noise ratio, which was related to channel coding, it was also a function of the probability of error. It was defined as here, the volume raised to the power of 2 over n is in the numerator, and I defined by sigma square of the noise, sigma z square, assuming I achieve the desired probability of error PE, which is the probability that the noise leaves the Voronoi cell. So if you have these two formulas in mind, you can see that what I'm getting is that the rate is this expression minus a loss, which is half log of the product of G of lambda 2, the coarse lattice, and NVNR, and it's the normalized second moment of the coarse lattice, and NVNR of the fine lattice. We want this loss to be small, of course, so we wish that this quantity would be equal to its ideal value. Do you remember what was the ideal value of the normalized second moment in large dimension? This is a famous 2 pi e, and so this should be 1 over 2 pi e, this should be 2 pi e, and then the product becomes 1, and we get that the loss goes to 0. But for any given two lattices, we have a certain quantity which represents loss. And here, what we get is almost the capacity of the AWGN channel. Again, we don't have the 1. Okay? But if we are working at high SNR, the 1 is not important, right? We don't need log of 1 plus something big is log of this something big. The ratio goes to, the difference actually goes to 0. Right? I mean, this is a small exercise to see that log 1 plus x minus log x goes to 0 as x goes to infinity. So at high SNR, we don't care about the 1. Okay. People like to define this quantity as shaping loss, log 2 pi e g of lambda, and coding loss as the ratio between u and 2 pi e, log and half. And then this loss is actually the sum of these two quantities. So the phi lattice plays the role of coding, so it is responsible for noise immunity, and we want that its coding loss would be small. And the coarse lattice plays the role, if we are working with normalized second moment, it reminds us of quantization. So the coarse lattice plays the role of a good quantizer, and we would like that its shaping loss, which is like quantization loss, would be small. So notice it is interesting. We have two lattices. Each one has a different responsibility. Okay. Now, I'm getting to something which would be maybe the story of today is okay. The story of alpha of somebody who is here in the audience. And there would be part 1 and part 2. Okay, and the part 1 and part 2 are opposite to how things happen in the history of research. But so I will explain it now that it is like become classics. But and then in the end I will tell you how the history really progressed. Okay, so we want this one. So it happened here. Maybe without, maybe it's better. Do I need a microphone? So if I speak like that, it's better with microphone. Okay. Hello. So we want this one. Why? One reason because in information theory we want to show that we achieve the limit. It's not enough to be almost. And the other reason is it's sometimes for some values of the SNR it is important. And in the end I will explain to you why actually this part is important. It is not important for high SNR, which we already saw, and it also is not important for low SNR. It is important at some medium value of SNR. But let's forget about practice now. We want to achieve the one inside this formula of the capacity. So what we do is add something here. So it's, since we are not doing maximum likelihood decoding, like approximating optimal decoding, so sometimes processing, some signal processing can help. We know that maximum likelihood is optimal, so it doesn't matter what we do, it will improve it. But if we do something suboptimal, then of course there are things that we can do that will improve the final result. So what we do, we say, we will put here estimation of x from y. And the estimator tries to minimize the estimation error between x hat and x. But what does it mean to minimize? What exactly we want to minimize, we will see soon. And here there is a crucial theorem or lemma which says that the system from here to here with the estimator, and here, by the way, the channel doesn't have to be AWGN for any channel, provided we are using a uniform random jitter. The channel from the cosine representative here and the output after modulo lambda subtracting of, after estimation minus jitter and modulo lambda is equivalent to this modulo additive channel. What is a modulo additive channel? We have input, we have noise which is independent of the input, and we have modulo operation. And what is this equivalent noise? Equivalent noise is distributed as the estimation error. Okay? So we can put there many kinds of estimators. Whatever estimator we put, we get some other equivalent noise. Okay? What is interesting actually is how it is true that this noise, the equivalent noise, is independent of the input. If there was here AWGN channel and we didn't put estimator, it is clear because we had AWGN noise which was independent of the input. But since we started putting here something which does processing, it's okay or okay, then it is surprising. It's working. Luckily, there are true engineers in there. So it is surprising that that in spite of the estimation, and I'm telling you even that for any channel which is not necessarily additive, due to the jitter we get a modulo additive noise channel. So it's very interesting, and it looks like a magic, but it is true, and actually it's true very easily. We just have that y tilde, as we know, it's given by x hat minus the jitter. Let's call it u minus u modulo lambda 2, and we can just add and subtract x. This doesn't change anything. And then we will keep the minus x as is, but this one we will write what it really is, which is the cosine representative plus the jitter. Mod lambda 2. We have here now, let's write x hat minus x minus u mod lambda 2. So what we will say now, we have two modulos. So the distributive property of the modulo operation means that we can ignore this one, and then jitter subtracts, it cancels out, and we notice that due to the crypto lemma, V is independent of x. And by data processing, or by Markov, since everything here is like a Markov chain, V must also be independent of x hat minus x, because x hat is a function of y, and y is a function of x. So we get that we simply have here V plus this, which calls the equivalent noise, modulo lambda 2. So this is a modulo additive noise channel. And again, this modulo additivity allows us to play with the analysis and apply all kinds of results from estimation theory, etc. So it is important. So this was the blackboard calculation. And okay, so now we say, okay, so the truth is that the optimum selection for the estimator is the one which will maximize, we want maximum capacity in this channel. Maximum capacity in a modulo additive noise channel means that we want the entropy of the noise to be, we want the noise to have large, small, medium entropy. We want minimum noise entropy actually, because the capacity of such a channel is simply log the size of the alphabet, which is the log the volume of the coarse lattice, minus the entropy of the noise. So we would like to find an estimator which minimizes the entropy of the equivalent noise. But this is very hard. I mean, I don't think you will find in the estimation literature how to find the filter or estimator which minimizes the entropy. This is very complicated. But we don't need that. We can simply use, again, linear theory, which tells us that if we are using simply a linear estimator, alpha, then the equivalent noise becomes, in this case, this difference, x hat minus x, becomes alpha z, because the IWGN was multiplied by alpha, and minus 1 minus alpha beta, which is the effect on the input here, x. The distribution of x is uniform over the coarse lattice, so it's the same as beta. And since it is independent of v, we have that this is actually the equivalent noise. The variance of this noise is what we care about, and it is given by this expression, and sorry, it is lower bounded by this expression with equality if and only if alpha is the alpha of Wiener. Alpha of Wiener, the famous formula, which is again SNR divided by 1 over SNR. And if we plug this in, so we just get the variance of this. We have a noise whose variance is this value, and the worst noise. What is the worst noise in terms of entropy given a specific variance? What is the worst noise for under a constraint on the variance? Of course, it is Gaussian. So we can subtract the entropy of a Gaussian variable with this variance, and we get magically the 1. Okay? So this is how we get back the 1 that we lost, minus the shaping and coding losses as before. Okay, so till now everything was very theoretical in the sense that we want the loss to go to 0, which means that the dimension goes to infinity. And if we are using construction A, there is a question: what happens if the alphabet of the code is finite and not going to infinity? K, I mean, construction A is defined by some linear code with K and N. So again, there are questions: what happens where things are finite? And another thing that was a little bit hidden is the fact that the jitter, what is the effect of the jitter on the noise, on the equivalent noise seen by the decoder? The decoder actually sees a mixture of Gaussian noise and uniform noise. If the coarse lattice is of high dimension, then this term is also Gaussian, because as we said yesterday, the jitter becomes Gaussian. So everything here is Gaussian, and it's okay. But if we're working in finite dimension, then the jitter is uniform. Suppose we are doing scalar shaping, the jitter is just uniform over interval. And we have here a mixture of Gaussian and uniform, and all this theory of what is the probability that the noise leaves the Voronoi cell needs to be, we need to look at it again when the noise is a mixture and not pure Gaussian. So it can be done, and in the end we get to the same conclusions. So it's more complicated, it's a little bit more ugly, but it can be done, and this is what I wrote here. The NVNR, the volume to noise ratio of the lattice and probability of error, also is a function of alpha. And about good pairs of nested lattices we talked about. What is the geometric picture? So maximum likelihood amounts to having decision cells which are open until infinity. So if I transmitted this point, all the y's that I will receive here will be matched to here because this is what maximum likelihood is. But we are doing lattice decoding, and lattice decoding means that we are, if we get a y here, we will map it to this point, which is not a valid transmitted point, and then we do modulo operation, which will take us here. So there is some inherent loss in this idea of lattice decoding, but the alpha fixes it a little bit, because what this alpha means. So what do we know about the alpha of Wiener? It is a number, it's not an arbitrary number, it's a number between 0 and 1. It usually does attenuation, right, of y. So we do attenuation, and then we do lattice decoding. We can think about it as if, instead of doing attenuation, we inflate the coding lattice, and we do coding with respect to inflated lattice code book. This is the blue picture. So these inflations help us to take y's which went outside and get a better probability that they will be mapped to the right point. So this is, I don't know, engineering way to understand why we need this alpha. This picture tries to show you what happens with the mixture. As I said, the mixture of Gaussian and uniform. An interesting point is that the best alpha was a winner for showing that we can achieve capacity. But a more elaborate analysis would be for error exponent. And it turns out that, and why error exponent is important? Because usually a system works at rates below capacity. And below capacity, what we expect is to get the lowest probability of error which is possible, which means highest error exponent. And it turns out that the best error exponent is achieved not necessarily by a Wiener coefficient. The Wiener coefficient is only optimal near capacity. This is the graph of error exponent versus rate for without alpha. With alpha equal 1, we got, you remember we got that we achieved half log SNR instead of half log 1 plus SNR, and the error exponent starts from here. So this is the error exponent of alpha equals 1. The red curve is the error exponent for alpha, which is the Wiener coefficient. But if we work at some rates below capacity, it turns out that some other values of alpha, let's say you see this orange, correspond to some other alpha, which is smaller than Wiener. It gives us better value, error exponents beyond a certain point. So if we can draw the curve, which is the error exponent for the best alpha for any rate. And the analysis, by the way, involves a large deviation, which I don't enter here, but with large deviation you can get the best curve of error exponent as a function of the rate. And it turned out that this error exponent with the best alpha achieved the Gallagher exponent for a power constraint channel, which is better than the green line. It's better than the red line. It's something which is the best of all worlds. So really, estimation here is something delicate. It's not necessarily mean squared error estimation. It's estimation which tries to give you the best noise for the problem, the best equivalent noise for the problem. Okay, let's skip this and next file, which is the last file. And oops, time was running amazingly fast. Okay, so site information problem. So multi-user information theory. So it turns out that all these tools are perfect now to be extendable to multi-user problems. And the basic problems of multi-user information theory are site information problems. One of them is source coding with site information, which means we have a source, we have site information which is correlated with the source, but only the decoder knows the side information. And there is channel with side information. So there is a channel which depends, which has some conditional distribution of y given x, but also conditional on some state s. And this s is known only at the encoder, but not at the decoder. So side information problems are these problems where one of the sides of the channel knows more than the other side. And this is very common in practice. For example, in radio fading channels, usually the encoder is ignorant of the phase. And in information embedding problems, we want to put digital data on a picture. The encoder knows the original picture, but the decoder only knows the encoded picture with the digital data which is hidden inside it. But more than that, hidden in every multi-terminal problem is a side information problem. For example, multi-terminal source coding, we have two encoders and a joint decoder. We can think about the code about an x and y are two sources which are correlated, but that they are encoded separately. The information that this encoder sends about x is like side information for this encoder which sends information about y. So this is distributed source coding, or multi-terminal source coding. Also in broadcast problem, let's look on the broadcast channel, famous broadcast channel where there are two users which want to receive information through the same channel by one encoder, which are, the information is encoded by one encoder. The information that the encoder sends to this user affects the channel, but the effect of this information on the channel is known at the encoder. So the encoder has knowledge about the state of the channel. So again, hidden in the broadcast problem is a channel coding with side information problem. Okay. And, well, there is not enough time, and I need to do something which is hard for me, to skip something. So let me just briefly talk about Slappy Wolf problem, because this is just very illustrative. Source coding inside information. So suppose, what does it mean in a question that we can think about? Suppose temperature changes in 1 degree from one day to another, exactly 1 degree. So the temperature today is either the temperature yesterday +1 or -1. And I heard the forecast for tomorrow, I know the temperature tomorrow, but I don't know the temperature today. I forgot to hear about today, but Raphael knows the temperature today, and I want to tell him the temperature tomorrow. Okay? So I would like to tell Raphael increase by 1 or lower by 1. So 1 bit of information. But I don't know what he knows, so I don't know if to tell him +1 or -1. So if there is a range of 8 degrees, so I need to give him 3 bits of information, which is a waste. But still there is a way that I will give him just 1 bit of information, and Raphael would know the temperature tomorrow. And this is if I know that the temperature tomorrow is an even number, and Raphael knows that it is an even number because he has an odd number. So I just need to tell him if my even number divides by 4 or not. Okay, so it's kind of 2 cosets. So I just tell him this coset or that coset, it's 1 bit of information. And this is the idea actually in Slappy Wolf problem, which is more general. There is x, which is encoded, and there is y, which is x passed through some channel, and this is side information. But it turns out that the ideas are similar, and we can prove them either by random coding techniques with random binning, and we could do that, but we don't have enough time, or we could do that with linear codes and syndrome coding. So it turns out that I can achieve the desired result, which is sending information at the minimum value, which is the entropy of x given y, although I don't see y at the encoder, but by just sending the syndrome, which means I just identify the coset of the vector x, and this is enough for the decoder who sees y and knows the coset of the syndrome to get x. And this is the idea of source coding inside information in the lossless problem. And you can see there is some analysis here with modulo operation, but it's modulo in binary codes. And we could do the same thing with, I will just skip it for a minute to source coding with distortion. This is the widest if problem. We could do it with lattices. But since time is running, I will jump to, we talked about here, so everything is in the slide that you received in the email. Right, Marcel? I mean, I guess people received here. Okay. But let's continue. So now we talk about part 2. And as I said, the history went in the opposite direction. So first, in the research of my PhD student, Uri Erez, we encountered the question of writing a dirty paper, which was solved by Max Costa in '83, long time ago. And there, the problem, it's a special case of the problem of channel coding with side information at the encoder. There is an IWGN channel, but there is also interference S, which is another additive noise. And this noise is known only to the encoder, but not to the decoder. And the magic was that as Costa showed, is that the capacity in this situation is the same as the AWGN capacity, as if this S didn't exist. And the proof was using random coding techniques, which is some kind of magic, but what it means in practice. And in the research of Uri Erez, okay, here is some example why it can be important. One example is related to this, why we call it dirty paper coding. So we have a paper which is full with dirt, which is kind of a picture. We want to hide in this picture, analog picture, some digital secret message. And only the encoder knows the original picture, or only I know the paper, the piece of paper with the dirt. I want to find a protocol between me and the guy that look on the dirty paper such that I will just do some small changes in the dirt. I don't want to erase it. It's too much power. And from these changes, he will look and he will understand what I'm sending. And in MIMO systems, this corresponds, as I said, to broadcast, multi-user MIMO broadcast, where suppose there is this antenna. Okay, this antenna only sends a wave to this user. He doesn't see this user, but this antenna sees both this user and this user. I would like to send information to this user by this antenna, to this user by this antenna, but there is this interference signal. So, but the encoder knows that what it transmits to this user, it knows the amount of interference. So it can try to do dirty paper coding to eliminate the effect of this interference from this antenna. So this is why dirty paper coding is related to broadcast also. So it turned out that the solution is take the lattice shaping scheme and simply subtract the interference before you do the modulo operation. If there wasn't here a modulo operation, subtracting the interference would cost us a lot of power, so we cannot do it. Suppose the interference has an infinite power. Still, the formula of Costa said it doesn't matter what the power of the interference, we get the AWGN capacity. So we cannot simply subtract the interference and say everything is good. No, we are losing power. But since there is a modulo operation here and there is jitter, the power here is always the second moment of the post lattice. And again, using the distributive property of the modulo operation, when you do analysis, this didn't exist, so S cancels out. And we get the AWGN channel. And we can also put the alpha if we want to, Okay, where is the alpha? We also can also put the alpha and get the same equivalent channel as we saw before. S cancels out. Okay, one word of caution. If we put here alpha, we must subtract at the encoder alpha S, so we can cancel out. Okay. Okay, so talking about the story. So what happened is that we were working. I mean, my student, PhD student, was working on trying to find a lattice interpretation or practical interpretation to dirty paper coding, and arrived to this solution. And then we realized, wait a minute, if there is no interference, we have a system that achieves with lattice codes half log 1 plus SNR. But in the literature, it was conjectured for many years that the maximum rate you can achieve with lattices is half log SNR. There is no way to get the 1. And so we published it as a separate paper, which attracted more attention because people are more interested in AWGN channel than in dirty paper coding. So this was how history went here in a very reverse way. So we started with the specific problem of dirty paper coding, and we arrived to something which was interesting for the conventional AWGN channel. Okay, so I skipped here many things, and let's see. You can now try to compare what's happening in Costa's paper in terms of random binning and what happens with the lattices and do associations. So it turns out that the binning becomes cosets. So each coset of the fine lattice, of the coarse lattice relative to by a shift from the fine lattice represents a bin. In the information theory language, a message is mapped to a coset. Typicality encoding, which was what's happening in the encoder in the random coding scheme, amounts to quantization or to modulo lambda operation. There is a meaning for U. Let's not enter this issue of the auxiliary random variable in the information theoretic solution, and typicality decoding became simply lattice decoding to the fine lattice. So it's interesting to compare, and in multi-user information theory, things very fast become very abstract. There are auxiliary random variables and things that work on the paper, but there is a question what it means in practice. So the connection is very important it's not important if it's lattices or not. Okay, so let's move on. So I promise you all kind of reasons why lattices are good in communication, a bridge from dimension 1 to dimension infinity, binning. There is this thing of joint channel coding that we will not talk about because there is no time, and Gaussian networks. So this is the time where I realized that the research about lattices is not only for the beauty or for the understanding, but also lattices sometimes give us better solutions than were expected by classical information theory. So this is where structure beats random, as it was mentioned yesterday. And I would like to ask with this picture, so find the differences. It's easy, right? You see that there are, I think, 2 differences as far as I remember between the picture. But we want to communicate the differences. So if one person looks on the 2 pictures and says, okay, there is difference in the nose and in the hair, it identifies the differences and then transmits the difference. This is easy. But suppose we are in a distributed scenario where one person looks only on this picture and the other person looks only on this picture. Each one needs to send information such that somebody that gets both messages will know the differences. So what do we do? I mean, I don't know what this guy is seeing, so what should I tell? I can tell the entire picture, but this is a waste of information instead of saying just nose and hair. So this corresponds to something which is known as the Kerner-Markov problem. So in the Kerner-Markov problem, there are two sources, X and Y, which are related by a BSC channel. And the BSC channel has a very small crossover probability. So each of X and Y correspond to one face. And the crossover or the changes between X and Y are the differences between the pictures. But instead of looking on X and Y together, each encoder sees one of them. But the joint decoder is only interested in the locations where the sequence of X's differs from the sequence of Y's. Okay, which is just a little bit of information. The entropy is very small. But how can we achieve it with two distributed encoders? I mean, we can just compress to each one compresses individually, and then do the estimation. Then we need to transmit 2 bits. Because X is Bernoulli half and Y is Bernoulli half. This is not good. We can do better compression, which is Lattice-Wolf coding, where one of them will send X as it is, and the other one will do coding of Y given X at the decoder. And then we will achieve a rate of 1 plus the entropy of Z. Z is the XOR between X and Y. So Z has a small entropy, but still we have 1. So let's say that Z has entropy 0.1, we compress to 1.1 bits. But this is not enough. So Kerner and Martin said, come on, if we could see X and Y at the same point, we could do the XOR, get Z, and then transmit only 0.1 bits. Can we achieve it? And they showed that if we are using linear codes and send the syndrome as if the same thing I told you about Lattice-Wolf coding, but each one will send the syndrome. There is due to linearity of the operation of getting syndrome from a vector, just multiplying by the parity check matrix, it turns out that I can calculate the syndrome of Z, which is what I'm interested in, and get with high probability from the syndrome of Z, I can get Z with high probability as long as there were not too many crossovers in the channel, typical crossovers. And the rate would be just sending the syndrome, which is 2 times the entropy of Z, which is 0.2. So I don't get the 0.1, but I get 0.2 bits instead of 2 bits or 1.1. So this paper was published in the end of the 70s, but it was forgotten. But there was hidden the fact that sometimes structure gives us benefit. The benefit that we are not going to get from random coding solutions. And now with lattice schemes, we could do the same thing where suppose there is X and Y, which are Gaussian, Y is equal X plus Z, and the decoder is only interested in Z, the Gaussian noise between X and Y. X and Y are very strong, Z is very weak. We don't want to waste too much rate, but the encoders are distributed. And you can do the same tricks of using lattices. Instead of sending a syndrome, we send the modulo information. Sending syndrome amounts to sending modulo information, and we can achieve what we want, almost what we want, by structured coding scheme. And one may ask, what is the problem with random coding? The problem with random coding, you can even see if you do lattice coding, but the lattices are not aligned. Suppose one encoder uses one lattice and the other one was a little bit different lattice. Then in this case, we will not get this phenomena of alignment or cancellation of things which are irrelevant and staying with the thing which is relevant. We will get ambiguity and it wouldn't work. Okay, this picture tries to show that what happens when two lattices are misaligned. And it turned out that the same ideas can work in other cases. So one case is what they call dirty multi-axis channel. So it's like the dirty paper channel, but now it's using a multi-axis scenario like this. two channels with each one has the dirty paper, but each encoder knows the dirt of its own paper, and the same ideas will work. And I don't need to tell you about this because this repeated many times in the talks. Lattice network coding or noisy network coding, and the same phenomena that if all the users can use the same lattice, we will have a phenomena that the code words are aligned, and we can remove noise which otherwise we couldn't remove. And the ideas even extend to interference alignment. This is the lattice network coding problem with relays. This corresponds to the interference alignment problem, where this was one of the breakthroughs in the last, I think, 5 years, that in the interference channel there is a way to suffer only one interference instead of many. And one of the ways to achieve this promise is by lattices, provided that we have some symmetries in the problem. There are many questions, and time is running, and I promised, so I was asked one question, so maybe you want Roseanne to repeat the question? Okay. So Roseanne, right? Ask me how these slides are being made. So one answer is that I'm drawing them on transparencies and then taking photos, but it's not this way. I'm just using tablet with a software which is called Journal, which allows you to do cut and paste and nice things. But I'm not sure I advise to everyone to use it. Sometimes it is easier than working with visual software, but in other cases it is harder. So it is my own game. And I think that we can say obrigado. So if there is time, I would be happy to answer questions, but maybe time is running. There is? Okay. So yes, please. In dirty paper coding, for example. Okay, so this was this picture. Okay, so this is the problem. The encoder is until this point. Okay, so if in this picture actually we have sorry, this is the encoder. This is the channel. So the y is given by x plus s plus z, and the encoder knows s, but the decoder doesn't know s. Okay, so this is the side information that the encoder has. Okay, now if the decoder knew s, it was easy. Just subtract s, and you eliminated its effect. But since the encoder knows it, s, and the encoder has a power constraint, it cannot subtract s. It needs to do something clever. And the idea was to do this modulo subtraction. So to do this, this is what you do. You just subtract what you know, then take modulo lambda 2, and then you transmit to the channel. This is how you use the information in this special problem. For other problems, you need to do something else. I mean, it depends what kind of channel and what kind of side information you know. Is it? I mean, I don't know if this is what you meant.
We have only a small set of modules maybe. So I mean that we have only a small set of operations which we can perform with these modules. So at first we should select some modules and only then select some noise.
I mean, the channel is given, it's not controlled by us. We are building the coding scheme. So suppose we are using a nested lattice coding scheme. And actually, I forgot to mention, this solution actually connects between two works which seem so remote. One is Max Costa's work about dirty paper coding. And in practice, people knew about something called Tomlinson-Harashima pre-coding. I don't know if anyone here heard about it. So this is a way to cancel intersymbol interference at the encoder instead of at the decoder. So this is more for the engineers, I guess. But intersymbol interference channel is a channel where you transmit symbols, but there is a filter that mixes them together. So how to get rid of it? There are many ways. One of them is by decision feedback equalization, which means that the encoder knows what it already, so the structure of the interface is usually causal. So if I succeeded to find previous symbols, I know their effect on the new symbol and I subtract it. This is decision feedback. Tomlinson and Harashima had an idea to do the cancellation of the encoder. So the encoder, if it knows the filter of the channel, it can predict the interference that the current symbol will make on the next symbol. So it can cancel it, but it cannot cancel it by subtraction because it will mean loss of power. So the idea of modulo of Tomlinson and Harashima was to do modulo, but they talked about scalar modulo, which was what people did in the early 70s. And there was this paper, and this work actually connects between these two different, papers and concepts. And it says that you can work with the lattice coding scheme. You have the coding lattice and the shaping lattice. And the shaping lattice can have small dimension or large dimension, whatever you like. And this is what is available to you. You can do modulo operation at the encoder. And the dimension of the coarse lattice will determine how complex is this operation, but this is something you can do. So what you do is you take the side information and you subtract it, and you do subtract it modulo the coarse lattice. So I hope this answers the concern. Yes, and this reminds me, by the way, usually in practice, we are willing to waste a lot of complexity on the coding side and less complexity on the shaping side. Maybe we don't want complexity at all. We want to work with scalar coarse lattice. So you would say it is impossible to mix the dimension. The coarse lattice and the fine lattice must be in the same dimension. But it turns out that you can do. You can work with the coarse lattice, just a Cartesian product of many simple coarse lattices, and one large dimensional fine lattice, and it can still work. So the complexity doesn't have to be the same for the shaping and the coding. Seems that people, I mean, I would be happy to get questions in the break, of course. So thank you very much.